Welcome to the solution of random MathStat problem number 188. In this problem, we're given a random sample x1, x2 out through xn, iid from the continuous Pareto distribution with parameter gamma. There are variations of the Pareto distribution, but in this course, our Pareto PDF looks like this. We're asked to find the distribution of the random variable capital Y sub I defined to be the log of 1 plus capital X sub I. Because the x's are iid, the y's will also be iid, so I'm just going to look at capital Y equals the log of 1 plus capital X and leave off subscripts. This is a G inverse problem. The transformation is y equals g of x equals the log of 1 plus x. The PDF for y is related to the PDF for x like this. We have already done this problem and reached the answer gamma e to the minus gamma times y and an indicator saying that y goes from 0 to infinity. Thus, we know that y has an exponential distribution with rate gamma. If you want to see more of the details in this ... section, check out the solution to random MathStat problem number 183. Let's move to part B. In part B, we want to find a 100 times 1 minus alpha % confidence interval for gamma based on the statistic, the sum of the logs of the 1 plus xi. We are asked to give our answer in terms of chi-squared critical values. As a reminder, the chi-squared n distribution is defined to be the gamma distribution with parameters n over 2 and 1/2. You may see this as gamma n over 2, 2, in which case your reference is parameterizing the gamma distribution a little bit differently than we are in this course. The sum as I goes from 1 to n of the log of 1 plus xi is simply the sum as I goes from 1 to n of the capital yi. We found in part A that yi has an exponential distribution with rate lowercase gamma, and we know by now that the sum of iid exponential random variables has a gamma distribution. The first parameter is the number of exponentials you add together, and the second parameter for that gamma distribution is the parameter for the exponential, in this case lowercase gamma. To try to make this look more like a chi-squared distribution, I'm going to begin by trying to turn this second parameter here into a 1/2. We have seen that if we multiply a gamma random variable by a positive constant c, we will get a gamma distribution again. The first parameter will be unchanged, and the second parameter will end up divided by c. So, if we want this second parameter to be 1/2, we need to multiply this statistic by 2 times gamma. In other words, 2 gamma times the sum of the log of 1 plus the xi has a gamma distribution with first parameter n and second parameter 1/2. To get it into this form up here, note that n can be written as 2n over 2. Now we recognize the chi-squared distribution with 2n degrees of freedom. To construct a confidence interval, we're going to need chi-squared 2n critical values. Imagine a chi-squared PDF and two numbers that capture area 1 minus alpha between them. It is not necessary to put this area in the middle, as this picture suggests. We could start our interval from 0 and many other numbers. Going with this picture, this critical value or number up here that captures area alpha over 2 to the right is called chi-squared sub 2n comma alpha over 2. If you are coming from a different course, you may use a different notation for this critical value. The critical value in our notation that captures area alpha over 2 to the left captures area 1 minus alpha over 2 to the right, and is therefore called chi-squared sub 2n comma 1 minus alpha over 2. This random variable here has this distribution, which means that if we put this random variable here between these two numbers, we will be in there with probability 1 minus alpha. As a final step, we want to look at this system of inequalities and solve for this lowercase gamma in the middle. This means I'm going to divide all the way across by 2 times the sum of the log of 1 plus xi. Note that the log of numbers greater than 1 is always positive, so we're not dividing by a negative and don't have to worry about inequalities flipping. Our final answer for a 100 times 1 minus alpha percent confidence interval for gamma in our Pareto distribution is given by this expression here. Other intervals that you might have gotten, depending on where you tried to capture area under the PDF, would be 0 up to chi squared sub 2n alpha divided by 2 times the sum of the log of 1 plus xi, or chi squared sub 2n 1 minus alpha over 2 times the sum of the log of 1 plus xi to infinity. And there are many more answers. For example, we might put area 1 minus alpha under the chi-squared 2n PDF between two numbers, where the first number captures area 1/3 alpha to the left, and the second number captures area 2/3 alpha to the right. There are an infinite number of ways we can capture the desired area under the chi-squared 2n PDF, but we have 3 common answers here, and we are done.